Okay, we are on chapter 25. This is section 1, definition of capacitance. Let's share the PowerPoint, and it opens up with a defibrillator. And what does a defibrillator have to do with capacitance? Well, it, like many other devices, needs a large discharge of stored charge very rapidly, and so this uh, this defibrillator has capacitors in it to store charge, and that's what capacitors do. They do other things, but uh, they are meant to store charge. If you have a digital camera or even uh, uh, an old camera, you can't fire off the um, the flash bulb repeatedly. There's usually some storage, some lag time where the camera has to store some more charge. I know on mine it's got a little flashing light, and the light has to stop flashing before I can take another flash photo. It's charging up a capacitor. So a capacitor is one of the three devices that we're going to study. We're going to study capacitors, resistors, and inductors. This is the first of them. When we build circuits, we're going to use those three devices. So a capacitor has the ability to store charge. Um, so when the capacitor is charged, the conductors carry charges of equal magnitude and opposite sign on either side of parallel plates. That's the typical image that we see of capacitors. There's all sorts of configurations. They can take those two parallel plates and roll them up into a coil, and they typically put some type of dielectric material in between them, both to insulate one plate from the other, but it also, we'll learn later in section, what is it? Section 25.5, that dielectrics play a role in increasing the charge that a capacitor can have. So the charge is equal to the capacitor times delta V, uh, the, uh, the electric potential. So the capacitancy of a capacitor is defined as the ratio of the magnitude of the charge on either conductor to the magnitude of the potential difference between the conductors. So capacitor, C is equal to Q divided by delta V. So, and the unit of capacitors, the unit of capacitance is the farad, 1 farad. 1 farad equals 1 coulomb per volt. Now, a 1 farad capacitor is a huge capacitor. We're typically going to work in 10 to the minus 6 microfarads. 10 to the minus 6 farads is microfarads. And that's going to be a typical, we're going to see values like 470 microfarads, maybe 470 microfarads, 33 microfarads, 330 microfarads. You'll see these values repeated, especially when we get into the lab. So we're talking small capacitance values. Not in my lab, you won't see a 1 farad capacitor. That's huge. Okay, when the capacitor is connected to the terminals of a battery, electrons transfer between the plates in the wire so that the plates become charged. Now I've got a little simulation here. Let's share. Where is it? Oh gosh, oh, here it is. Okay, this is over here, what just turned blue, that's a battery. The symbol for the battery is a short horizontal line and a longer horizontal line above it. This over here is a capacitor. It signifies the plates. They're of equal value. And this down here is a resistor. We'll get to these symbols later. So we've got some value here. I don't know. Let's see. Does it say what the? It'll tell us once we charge the capacitor. Once we've got 200 microfarad capacitor, And once it charges up, we'll probably see the value. And I gotta run. Okay, so it's charging up. It's charging up the capacitor. You can see the little yellow dots are slowing down because it's fully charged. It's about 5 volts. There it is. It finally reached 5 volts. And if you notice the bottom, there was a charge. There was a charge curve on it. Now let's flip the switch, and you can see that it discharges. There we go. There now it's discharging. You can see the green line is the discharge. It's going from 5 volts down to 0 volts, and we can change. There's such a thing as a time constant. We're not going to worry about the time constant just yet. We'll get to that when we get to resistors. Actually, we're going to be doing a little experiment with time constant just to show you. But now let's increase the capacitor to 400 microfarads. So we've increased the capacity. So let's reset and turn it on. Now it's still going to go to 5 volts because that's our source. Our source battery, and it's charging up. It's 4.89, 4.9, and it'll eventually get up to 5 volts. So it slowly charges by building electrons on one side and having a paucity of electrons on the other side. It leaves what is called holes, which makes it positive. And then we flip it, and it doesn't say the charge on it, but let's flip it, and it might. It doesn't. It gives you the current and stuff, but it's discharging now, and you can see the green line is going down to 0. So that's the a capacitor charging and discharging. Now let's go back to the PowerPoint, and there's the PowerPoint. Okay, so that when you connect it to a battery, you get electrons on one side and holes on the other, so that it's positive. There's an excess of protons on one side, an excess of electrons on the other side. Okay, a capacitor stores charge Q at a potential difference delta V. What happens if the voltage applied to the capacitor by a battery is doubled to 2 delta V? The capacitance falls to half? No. The capacitance and charge both fall to half their initial values? No. The capacitance and charge both double? No. The capacitor is going to remain the same because the capacitor is determined by its physical properties, the area of the plates, the distance between them, whether there's a dielectric in between the plates or not. So the capacitance is going to remain the same, but the charge, since it's 2 delta V, the charge is going to double. And that ends this first section, 25.1. And next we'll go to calculating capacitance. I have to show you the answer. The capacitance remains the same and the charge doubles. And then next we'll pick up at calculating capacitance.